Hello, my name is Marcia Smith and this is my presentation on the Great Basin National Park. I hope you enjoy it. Great Basin National Park is located in eastern Nevada near the Utah border in White Pine County. It was officially protected with national park status in 1986 and has a fascinating geologic history that spans millions of years. In this presentation, I'm going to provide an overview of the overall geology that formed the park because this is a unique and important feature. I will also cover Wheeler Peak and its quartzite mountain building, the park's moraines formed by glaciers, and the formation of Leavens caves. But first, let's watch a video that provides a brief overview of this hidden jewel.
The Great Basin stretches from Utah's Wasatch Mountains to the Sierra Nevada in California, in one endless reach of mountain ranges and wide valleys. At the center of this immense region, in the South Snake Range, Great Basin National Park protects the jewels of this country. Some of its highest mountains, its most spectacular caves, and some of the oldest trees on Earth.
First, let's talk about how the Great Basin was formed and its geology in general. The huge U.S. Great Basin region, which contains the Great Basin National Park, offers a captivating geological history spanning millions of years. Here's an overview of its development. Paleozoic, 540 to 250 million years ago. During this time, the region that would become the Great Basin National Park was submerged beneath the shallow sea. Sedimentary rocks, including limestone shell, were deposited in the marine environment and became thousands of feet thick. Mesozoic era 250 to 66 million years ago. The sea retreated and the area underwent significant uplift and deformation due to the tectonic forces. This tectonic activity formed the foundation of the modern mountain ranges in the Great Basin region and occurred via intense heat from the Earth's mantle and dozens of active faults. Sedimentary rocks were further deposited, including sandstone and conglomerate, as rivers and streams carried eroded material from the uplifted mountain. Cenozoic, 66 to 2.6 million years ago, heat and pressure from the Earth's mantle forced the crust to stretch and thin throughout this huge area. This process is known as rifting. Then the basin and the range experienced extensive faulting and block faulting, leading to the formation of numerous mountain ranges separated by flat valleys called basins. This occurred in a distinctive pattern: basin range, basin range, basin range. After this modern geography of the Great Basin was set, however, the Ice Age played a huge role in the weathering of the landscape into its existing appearance. Glaciation played a crucial role in shaping the landscape during this Pleistocene time period, 2.6 million to 11.7 thousand years ago. Glaciers carved out valleys, polished rocks, and left behind moraines and other glacial landforms. The Great Basin that the national park is named after covers a massive area. It extends from the Sierra Nevada mountains in California to the Wasatch Mountains in Utah, and from southern Oregon to southern Nevada. This graphic serves to highlight the huge region that its unique geology covers. Great Basin National Park is relatively small compared to the overall basin region. However, it serves as a strong example of what is found throughout the region, a distinct pattern of basin range, basin range, basin range. And did you know that none of the rain or snow that falls here will ever reach an ocean? Instead, it remains within the basin and deposits into lakes, rivers, streams, and underground aquifers. Now let's talk about the biggest landmark, most famous feature, and highest mountain within the Great Basin National Park, Wheeler Peak, which is part of the Snake Mountain Range. The mountains located within Great Basin National Park, including Wheeler Peak, were formed of sediment-like sand, mud, and limey ooze, silt and clay particles mixed with calcium carbonate. These sediments were deposited at the bottom of a shallow sea millions of years ago. As layers stacked upon layers, these sediments were turned into sedimentary rock. Sand became sandstone, mud became shale, and limey ooze became limestone. These layers were further changed during the mountain building event around 200 million years ago. Geological activity, immense pressure caused the layers at the bottom of the stack to metamorphosize slightly. Sandstone changed gradually into quartzite and limestone to marble. Magma also rose from deep within the earth and pushed its way up into these layers. It did not come to the surface, however. Staying underground, it cooled and became granite. The modern Snake Mountain Range, including Wheeler Peak, finally began to take its current form around 30 million years ago. The Earth's crust in this area began to stretch in an east-west direction, known as rifting. Bedrock nearest the surface reacted to the crustal stretching by breaking into immense blocks several miles wide, tens of miles long, and thousands of feet thick. Many of these blocks fractured into pieces and tilted and spread out like a row of odd-sized books sliding out of place on a shelf. The rifting formed the current Snake Mountain Range because the stretching occurred in an east-west direction. This range lines up in a north-south direction. Wheeler Peak is the most prominent peak in the park surrounding area and second most prominent peak in Nevada, just behind Mount Charleston. Thanks to geological and glacial activity that occurred during the ice ages, Wheeler Peak has an impressive head wall above a large glacial cirque, large moraines, and an active rock glacier. As a reminder, a cirque is an amphitheater-like valley formed by glacial erosion, and head wall is the highest cliff of the cirque. We will discuss Great Basin's fascinating moraines in future slides. And now let's discuss moraines. They were formed during the Ice Age and are a key feature of the park. Glacial geology also played an important role in the formation of Great Basin National Park. Between 2.6 million and 11.7 thousand years ago, glaciers covered out valleys and polished rocks and left behind moraines as well as other distinct features. Glaciation is responsible for creating and weathering the current landscape and topography into its existing appearance. One of the unique glacial features highlighted with Great Basins are moraines. Moraines are geological formation created by the depositation of rock debris and sediments carried by glaciers as they advance and retreat across the landscape. As glaciers move, they erode bedrock through processes like abrasion and plucking, picking up rocks and debris along the way. When the glacier's forward motion slows or halts, either due to a decrease in the ice volume or a change in climate, it deposits the accumulation debris in the form of ridges or mounds. These deposits, known as moraines, are typically composed of a mix of different sized rocks, gravel, sand, and clay. During the ice era, glaciers carved through landscape, leaving behind moraines that now dot the park's terrain. The moraines serve as a tangible evidence of the park's glacial history, revealing the dynamic interplay between ice and landforms over the millennia. Today, they provide scientists and visitors alike with a window into the park's geological past, offering clues about an ancient climate and environmental conditions. I saved the best part for last. I have always loved Lehman's Caves, and that's why I chose the Great Basin National Park for this project. Now, let's find out how they were created. Now for the crown jewel of the Great Basin National Park, Lehman's Cave. Due to its underground location, the caves are always a constant 55 degrees and open to public tours year-round. If you have never visited, I strongly encourage making the trip. The basic geology of Lehman's Caves can be broken down into three main parts. Part 1, formation of the limestone. The rock layer that formed Lehman's Cave began as limestone that originated from warm, shallow sea about 550 million years ago. This limestone layer was covered and uncovered periodically due to plate drifting and other geological activity. When a huge basin and range area was made, the rock was put under a lot of heat and pressure, making it into a low-grade marble. The mountain building phase of the park that we previously discussed created many fractures in the rock. Part 2, dissolution of the rock to make a cave. Warm acidic groundwater entered cracks in the rock and dissolved away passages and rooms. This left huge voids in the rock and occurred near the top edge of the water table. Many refer to this as the hollowing out phase. And Part 3, deposition of speleothems. The third and final phase leading to the caves in their current form can be called the filling in phase. The water table dropped, and as the surface water percolated through the soil and organic debris, it became slightly acidic. As this weak acid water worked its way down, it dissolved away part of the marble above the cave. When the catalytic-rich water reached the air-filled passages, it deposited speleothems of many types. Some common speleothems are stalactites, stalagmites, and columns. The beauty of Lehman's Cave and its fascinating geology will now be discussed in a brief video clip.
The age of Lehman Caves is estimated to be between 2 to 10 million years old. During that time, warm water that was naturally rich in sulfuric and carbonic acid rose beneath the mountain. Once that water encountered the marble bedrock, it dissolved the rock until it created these passageways and rooms. Eventually, the water table lowered, providing the opportunity for water from the surface to enter the newly created space and begin to develop many of the formations called speleothems. Looking to the ceiling, we can see icicle-like structures called stalactites. On the cave floor, we can see formations growing up towards the ceiling. These are called stalagmites. When stalactites and stalagmites grow together, we call the resulting structure a column, as we can see on the left. If the labels prove difficult to remember, a good verse to have in mind is, stalactites have to hang on tight. Stalagmites, you might trip over them, and together, you call them a column. No matter how or what you use to remember the names of different speleothems, they are just one of the phases of the geologic development of the cave.